Hi, it's Mr. Bennett. In this video, we're going to talk about what evidence we have for plate tectonics. So what evidence do we have to support this hypothesis that that the continents are moving around on these giant plates that are floating around on the asthenosphere? So to talk about this, first off, I'm going to introduce the guy who first came up with the hypothesis of continental drift, and it's a guy by the name of Alfred Wegener. Now, Wegener was a German meteorologist, so someone who studies the weather, but he made some key observations that led to the first hypothesis of continental drift. And he came up with all this in 1915 is when Wegener came up with all this stuff. So what Wegener's idea was is he went and he looked at the continents and he saw evidence that at one point all the continents were together in one piece. And so by seeing that all the continents were at one point in one piece, and now they're obviously not, that's where the hypothesis of continental drift came from. Now, the terms of the continents all being in one piece, you're probably familiar with this idea of Pangea, that 250 million years ago, all the land on Earth was in one supercontinent. So there was no Asia, Africa, Europe, South America, Australia. All the land was together. You could walk from one piece of land to another piece of land all over the Earth. So, as mentioned, you've probably heard the term Pangea before. Now, the one thing you may not have thought about is if there is only one continent, then that means there's only one ocean as well. And that single ocean that surrounded Pangea we call Panthalassa. And that's something you should probably remember. This is the single ocean that surrounded Pangea. And Wegener was the first guy to come up with these terms. He was the first one to make the suggestion that all the land was together in one piece called Pangea. And as a result of that, all the water was together in one piece called Panthalassa. So what led Wegener to his idea that all the land was together in Pangea at one point? What evidence do we have that all the land was together in Pangea? Well, the first thing he noticed is that if you look at the Earth's continents, some of you may notice before, that some of Earth's continents look like they would just fit together perfectly like a jigsaw puzzle. The most common example is here. South America looks like it would fit just perfectly like a jigsaw puzzle into Africa. And you can see that in this drawing down here, that if you take a map of South America and you take a map of Africa and you put them together, they're almost a perfect fit. Now, there's some areas where there's some gaps because of erosion and so forth that way, but South America and Africa were definitely together as one land piece that broke apart, 250 million years ago. Another one that's pretty famous is the east coast of the United States is a pretty good fit there for the northwest corner of Africa, as you can see in this picture down here. That at one point, the east coast of the United States was butted up against Africa, and they were one piece, okay? Spain was once hooked up to Africa. That isn't too hard to get your mind around and so forth that way. So that was the first piece of evidence that Wegener came up with, that all of the Earth's continents, if you cut them up, you can pretty much put them together like a jigsaw and see how they once fit together 250 million years ago. Now, we have evidence beyond just the fact that the continents look like they would fit together like a jigsaw puzzle. Some more evidence that we have of plate tectonics, that the continents are actually moving, is we have found fossils of the same species spread across different continents. So, for instance, let's talk about this guy right here, Leistosaurus, and here is a fossil of Leistosaurus right there. You can see in this picture here that fossils of Leistosaurus have been found in Antarctica, they've been found in India, they've been found in Africa, they've been found in Madagascar. Now, if the continents were never together in one piece, what that would mean is that this species would have had to have been able to swim from Antarctica to India to Madagascar and Africa, because you can find this exact skeleton right there on all of those different pieces of land. Now, if you look at that, does he look like a good swimmer to you? Heck no, all right? And so the only possible way to explain why we find this fossil on all these different continents is that they had to be together in one piece at one point. Here's another one, Sinognathus, right here. This is a skeleton of Sinognathus. You can find fossils of this guy all throughout South America and then right there in Africa. And if you put South America and Africa together the way they should fit, like a jigsaw puzzle, you'll notice that the range where we find this fossil is a perfect lineup right there. Okay? Check out this plant right here, Glossopteris. It's found in Australia, it's found in Antarctica, India, Madagascar, Africa, and South America. You can find fossils of this plant in all of those different land masses. Once again, can a plant swim? Heck no. And so the only way that this plant could have existed on all these continents at the same time is if they were all together at some point. And so the fact that we find fossils of the same species on two different continents is pretty good evidence that the continents were together at some point. Now, not only do we find fossils for the same plants and animals spread across on different continents, we also find that we have similar rocks that are found on different continents. And so what you got going on here is that we found that on different continents we find rocks that are of the same type and they're the same age, but they're found on two different continents. So if you look at the east coast of the United States, you have the Appalachian Mountains there. They're made out of a certain type of rock that's a certain age. Well, guess what? Over on Africa, where Africa would have been attached to North America back in the day, we find that those rocks are the same age and the same type. And so the rocks here on two different sides of the Atlantic Ocean are a perfect match for each other. They're the exact same type and they're the exact same age. We see the same thing here going on with Greenland. That the east coast of Greenland is a perfect match for the Caledonian Mountains. They're on the west coast of Norway. And so the only possible explanation for this is these two pieces of land had to be together at some point. That's the only way you can get the same age of rock and the same type of rock found on two different sides of an ocean. Once again, coming back to our example of South America and Africa, you can see the same thing here. Here you have this whole big type of rock that's found here in Africa, and you find a piece of that that's identical to it here in South America. You find this type of rock here in Africa. You find an identical piece to it there in South America. And so if you take and you look at the rock types in Africa and South America, you can see you can find exact matches for them in the opposite continent. And once again, the only way you can explain this is that Africa and South America had to be touching each other at some point. Now we're still not done. We have even more evidence that plate tectonics happen. The reason why I'm giving you so much evidence is the idea that the continents are moving is a pretty big one, but we have lots and lots of evidence to back it up. So even more evidence that we have that the continents were all one piece together is we can look at glacial scarring. Now a glacier, if you don't know, is this. Okay, that's a small glacier right there. They're basically a river of ice that is moving. And so this glacier right here is constantly moving downhill towards the water. Now, as glaciers move, because they're heavy and there's a lot of weight going on there, they actually scar the landscape. They carve it out. They kind of like dig it out. And what you're looking at here is this is glacial scarring. That at some point, 10, 15, 20,000 years ago, this whole area here was covered by ice. It was covered by a big glacier, and that glacier was moving. As it moved, it dug these big, caverns or, grooves or whatever you want to call it there in the rock, all dug out of the rock by the glacier moving through it. So that's what we mean by glacial scarring. This is glacial scarring over here. Well, what we've noticed is if you look at South America, Africa, India, and Australia, and Antarctica, you find the same glacial scarring on all of them. That what happened was at some point all of these different land masses were together and they were all covered by the same glacier. So this white area here represents the glacier that covered all these land masses. And what you see is this glacier was moving in all these directions at the same way, and as it did that, it left behind glacial scarring. So if you look at this part here of South America, you can find glacial scarring. If you look at this part here of Africa, you can find glacial scarring. Now this part of Africa right here is a rainforest today. So the idea that there was a glacier there at all gives you an idea that Africa's moved, because there sure as heck aren't glaciers there today. But the glacial scarring here on Africa is identical to what we see in South America, India, and Australia. And so this is another piece of evidence we have that the continents have moved, that they were once in one piece, because all these different continents have the same glacial scarring to them that was created by the same glacier. And so that is more evidence that the continents have moved, because we have evidence that these continents were together at one point, and since then they've moved apart. All right, the last piece of evidence I'm going to give you for plate tectonics, the last piece of evidence that Wegener had to work with, is speaking of climate change. In the last slide I talked about how Africa used to have a glacier on it, and now parts of Africa that are jungle used to be frozen. Well, you can take the other extreme. In Antarctica, you think of Antarctica today, complete frozen wasteland. On Antarctica today, there's a mile of ice. The ice in Antarctica is a mile thick. Well, guess what? It wasn't always that case. Antarctica used to be teeming with life. It used to be very, very diverse climatically. That you used to have areas that were forest, grasslands, deserts, and so on and so forth that way. So there used to be jungles on Antarctica. Now, there's no way you can have a jungle in Antarctica today, because it's all the way on the bottom of the earth. It's down on the South Pole, and that makes it very, very cold. But back in the day, Antarctica used to be much, much further north, hooked up to South America. When it was hooked up to South America, that made the thing warm. And so the fact that we have evidence that Antarctica used to be a jungle is pretty good evidence that Antarctica has moved, because there's no way you can have a jungle where Antarctica is today. The only way that came about is because Antarctica used to be in a different place where it was warmer. All right, so that wraps up this video on evidence for plate tectonics. This is all evidence that Wegener had to work with. In our next video, we're going to talk about seafloor spreading and paleomagnetism. This is the stuff that definitively proved that plate tectonics happened, and that came about in the 60s. But we'll get into that in the next video.